Hello everybody, my name is Szymon, and I would like to welcome you on our event on the NAFEMS Eastern European 2020 Engineering Simulation Virtual Conference. And today I would like to show you a brief presentation about a case study of metal to plastic replacement for automotive applications. And to be honest, at the very beginning I need to make some kind of disclaimer, because my presentation is not going to be very detailed. I'm not going to show all the setups and all the results that I gathered during the whole process of the metal to plastic replacement idea. The whole presentation has a main goal of showing you the workflow and how to use the tools and what exactly tools are needed to have this replacement done successfully. So that's the agenda of today's presentation, and at the very beginning I need to briefly describe my employer, namely the Black Cat Engineering company, and after that I will try to make a rough sketch of the background of the whole project, because all of you probably would like to know what kind of part I'm going to check, to analyze, to simulate, and why I'm doing that in such a way. And straight after that we will go to the point of the presentation of the topic. So we will just discuss the whole idea of metal to plastic replacement, what needs to be done, how you should do it, in which order, and so on. Hopefully you will find it helpful. Black Cat Engineering is a company which provides a very range spectrum of CAX services, so CAD, CAM, and of course CAE, which is my personal area of interest, for different types of industries, from aerospace to packaging. The company has two offices. One of them is in Western Poland and the other one in Western Germany. But of course, right now, most of us work from home. Probably all of us are aware of the whole eco-trend in the automotive industry, the idea of being more environmental friendly and build more sustainable systems in the whole automotive branch. And one of manifestations of such idea, the so-called 48-volt eco-drive system, which is mainly based on energy recuperation. The system recovers the energy from the combustion engine during the situations like stopping of the car. So if the driver hits the brakes, instead of losing the momentum which is still inside the engine, the system transfers the energy to an additional battery, and the energy which is stored there is later used as a power for the whole onboard devices like car audio and so on, and can be also used to power up the electrical engine in a hybrid vehicles. And the system was designed by Vitesco Technologies, formerly known as Continental, and it was already used in cars like this Audi A8. The heart of this eco-drive system is so-called belt starter generator. Is a device which replaces two other devices which were formerly used in traditional combustion cars, namely the starter and the alternator. And if you look under the hood of this Audi A8 vehicle, you'll probably see such a device. So an assembly from parts made almost only from metal, from aluminum in this case. And if you really would like to look under the hood of this car, you will see the device, the belt starter generator, mounted close to the engine, of course, and on the main transmission belt of the engine. And because of that, the whole assembly of this belt starter generator is mainly loaded from the forces generated by this belt, so by an oscillating force. And as you can see right now, almost all the main parts of the assembly are made from metal, from aluminum, But our job today is, of course, to replace the metal parts with the plastic ones. And during this presentation, I will going to describe the process, this metal to plastic replacement for this particular part. So for the front half of the housing here. Okay, so just let's do it. Let's take the metallic material from the part, and instead of it use the polymeric one. But I think almost everybody knows that the things aren't so easy here, and it is impossible just to take the old design, the old geometry, and use the new material, especially when it is a polymeric material, and just to produce new parts. Because, as you can see here, the wall thicknesses in this particular part vary from 3.5 millimeters to almost 12 millimeters, which is, of course, mildly speaking, unsuitable for injection molding, and it will lead to huge warpage and make the part just not acceptable by anybody. So if we cannot use the old geometry, the old design, we need to make a new one. And to do so, we just start with a shell model with a constant wall thickness suitable for the injection molding, and we perform a so-called topology optimization to look for the new geometry for the structure, like these ribs here, which were suggested by this simulation, by the optimization, and they are obviously needed to fulfill the structural demands for the part. Even though we design our geometry according to this DFM rules, so with a constant wall thickness, we still need to double check it with this injection molding simulation, because as you can see here, it appears that our well-designed geometry has a post-molding deformation warpage of almost 2.6 millimeters in this specific area here. And of course, with software, with Model X3D, in this case, we can not only predict the displacement, the value of the warpage, but we can also try to avoid it by changing our geometry. And as you can see here, that's exactly what we did. By changing the geometry of the ribs of some areas near to the balls, we reduced the warpage almost by 50%, from 2.6 millimeters to 1.5, and keep it in the acceptable range. And now, if we have our geometry, which is fully prepared for the manufacturing process, for the injection molding, we can move to the structural analysis, to the frequency response and numerical simulation of our part, because the main force, the main load for our design is the force generated by the transmission belt of the combustion engine. And as you can see here on these pictures, the values of stress and strains aren't very worrying. They aren't above the limits which were set up by the producer of the material, because here we are using PA66 with the 30% of fibers of the fiber reinforcement, and such values are still okay, are still acceptable. So, are we done here? Are we ready to produce the part? Of course not. And why not? The key to the answer is this one letter word here, namely isotropic. We cannot assume that our polymeric material or composite after injection molding is going to have fully isotropic properties. Such assumption on this stage, to put it mildly, isn't a good idea. We always need to take into account the orientation of the fibers in our part after the injection molding process. But which orientation is the right one, and which one we should really consider during our structural analysis. To answer the question, it is always good to use some kind of optimization tool like DOE, which is embedded in Multex 3D software, in which we can specify our parameters. In this case, they are different models with different gate types for our geometry, different filling times, and mod temperatures. In my opinion, these three are the parameters which have the largest impact of the fiber orientation in the molding. And of course, we need to also define a quality factor. In this case, we need to use some kind of substitute for our fiber orientation, because right now it's impossible just to directly define fiber orientation as a quality factor for the DOE analysis. So we used shear rate in this case, which in my opinion is directly coupled with the fiber orientation, and it can be used in such manner. And as a result of this optimization of the DOE, we have the whole response surface, on which we can see how specific parameters affect our quality factor, our shear rate. Right now we are looking for the minimal value of the standard deviation of the shear rate in the part. So looking for the most blue one, most blue points on our graph, on our surface here. But of course, we do not need to analyze it manually or by ourselves only. The program gives us the whole results and finds for us the optimal setting, which in this case looks like that. The model looks like that, the model of the gate. So we need to use this type of gate, so-called spider gate, to have the best possible fiber orientation, and the values of filling time and mod temperatures are like this one here given. And to double check the results of this DOE, of this optimization, it's also good to compare this best result, this optimum, with the worst case, which is in this situation for this specific case, the one here. So with the filling time of 1 second, mod temperature 75 degrees, and with a direct hot runner gate, hot drop on the part. And as we can see here, there is a clear difference between the optimal and the worst setting. We can see it here in this area. These two are the results of the e-modules after the molding, the values of the mean modulus in our part. And as we can see, we have a more uniform distribution of the value of the modulus for our optimal setting. That's the reason it is optimal. So at the point, we know that we need to perform our frequency response analysis, and we found already the best fiber orientation for our part, for the geometry we have designed. But there is still a gap to be bridged. Namely, we need to transfer the results of our injection molding simulation to the input of our structural analysis. But right now we don't need to find the way how to do it. There is a already designed, made, and invented solution for that, namely Digimat, the software which helps us to bridge, to combine the two worlds of manufacturing and structural simulations. The program allows us to map the properties like fiber orientation from our manufacturing mesh, which is here on the right, to the structural mesh, which is here on the left. Here we have the whole assembly prepared for this model analysis in Abacus, and on the right there is the result from Moldix 3D injection molding simulation. So that's the first thing, very important, that the program allows us to map the fiber rotation, weld lines, and other properties from one simulation to the other one. But it also provides us with the material model, which is able to use these properties in the structural analysis, which is probably even more important than only the properties which are being transferred from injection molding to structural simulation. And here we can observe the results of the model analysis with and without the material mapping done previously with the Digimat software. In this case, we would like to find the four first modes of our system, and of course analyze the shape of it. And as you can see here, for all four modes, the shapes are pretty much the same, as well as for the isotropic and the anisotropic material data. So the displacement, the direction of the displacement is the same, and the amplitude. So the situation is pretty much similar for the second mode, for the third mode, and probably, as we can predict also, and as we can already predict also for the fourth mode. But the natural frequencies of all these modes are the same. We can see it clearly in the table here that for all the modes for anisotropic material, the frequencies are smaller than for the modes of the isotropic material simulation, which of course means that our system is less stiff than we previously predicted in our first simulation done with the isotropic data. And also the results of the next simulation and the frequency response analysis will also be different from the previous one, which corresponds with all the results found in these references here. In all these cases, people found that there is a difference in stiffness, natural frequencies, and resonance peaks after mapping the properties from the injection molding simulation. I would really like to show you the one-to-one comparison between the experimental result and the result of the structural analysis. But the experiment hasn't been done yet, so at some point we just need to believe that our results, our simulations are correct. And looking at these cases here, we can assume that they really are. So, to sum up, don't be scared to use plastic materials, even though they are right now treated almost like a toxic waste, and people are trying to remove it from any other applications. You can always make something better from the polymeric materials, something more environmental friendly, lighter, and something which is going to be produced in a less energy consuming process. But please do not redesign the old geometry. Please do not redesign the geometry of the part which was formerly made from metal. You always need to start from the beginning. You always need to start from the topology optimization. After that, make a first round of a structural analysis, even an isotropic one, just to check if you are still in the range of your tolerance of the stress and or strain. After that, make a loop of injection molding simulation on any other manufacturing simulation to check if your geometry still adhere to the design for manufacturability rules and just optimize it in case of large warpage and pressures and so on. And mind the gap between the results of your injection molding simulation and the results you would like to have from your structural analysis. Mind the gap and bridge it. Bridge it with software like GMAT-RP or any other material modeling platform. Because it is very important, it is crucial to take into the account to transfer all the manufacture process induced properties of your part from the manufacturer simulation to the structural simulation. Because without that, especially in the process of metal to plastic replacement, without that you would just end up with the wrong results, with the faulty analysis, and it can lead to a very, in some situations, it can lead to a very dangerous repercussions. Thank you very much. That will be all for today. Thank you that you are still here. I hope that you enjoyed the presentation, even though it was a bit overall. Like I said at the beginning, I didn't show any specific meshing techniques or solver setting and so on. But you can always ask me about it. Yeah. Just contact me directly via this email address, which you can see here, or visit the website to find more information. One more time, thank you very much for your attention, for your attendance here at the conference. See you and take care. Bye.